question is, how many factors of 4 to the power 5 times 5 to the power 4 times 6 to the power 3 are perfect squares but not perfect cubes? Right, so now in these kind of questions, firstly, write the number in the prime factorization form. So 4 to the power 5, we can write it as 2 to the power 10, and then 5 to the power 4 times 6 to the power 3 can be written as 2 to the power 3 times 3 to the power 3. Now, as the bases of these two numbers are same, we can write it as 2 to the power 13 and then the rest of the number, right? Now, firstly, you have to understand what is a perfect square factor standard form. So perfect square factor in these kind of cases, in these kind of prime factorized number, it can be like a to the power 2, b to the power 4, c to the power 6, or like b to the power 2, c to the power 4, or like an individual number such as a to the power 8, right? All of these can be the factors. Now, to check if the number is perfect square or the factor is perfect square or not, all you have to say is if the powers are divisible by 2, that means all the powers of a particular factor are divisible by 2. That means the factor is perfect square, right? Like all of these powers are divisible by 2. This is a perfect square. Same for this, same for this. Now for perfect cube, again, it can be like a to the power 6 times b to the power 12, right? It can be in any form. Now to check for perfect cube, the power should be divisible by 3, right? So now here 6 is divisible by 3, 12 is divisible by 3. That means this is a perfect cube factor. Now, in case like one of the number, for one of the number, the power is not divisible by 3, that means it is not a perfect cube, okay? All the power should be divisible by 3 in order to make a perfect cube. Alright, so now what we have here is, looking at this prime factorization, we can write some individual numbers, right, which are a perfect square and a factor of this number, such as 2 to the power 2 will be a perfect square factor for the number. Same for 4, 6, 8, 10, and 12. Right, now for 3 it will be 3 to the power 2. For 5 it will be 5 to the power 2 and 5 to the power 4. Right, now in order to find the combinations, right, we have to find all the combinations, right, because these are the individual factors. But when we take product of any two numbers or any three numbers, right, like this, like 2 to the power 2 times 3 to the power 2, this is also a perfect square factor of a number, right? Also, you may think that 2 to the power 2, 4 times 2 to the power 6 is also one of the combination of perfect square, but we have already considered it when we are taking 2 to the power 10, right? Because if bases are same, we can add the power, right? So we don't have to take the combinations of similar base number, right? We only have to take the combination with the different base numbers, right? Now, in order to make the combinations, firstly write 2 to the power 0, 3 to the power 0, 5 to the power 0 here. Now, why we are doing this, I'll tell you later. But before that, let's see how we are making the combinations. Alright, yes. So now, let's say this is the first number. So we are taking this, then this number, then this number. Similarly, first number, this number, then this number. This is the second combination. Again, this number, and this third number. This is the third combination. Now again, the first number will be same, but here we are taking 3 to the power 2, and then same 3 different combinations with the power of powers of 5, right? Now you can see with each number we are getting 6 combinations. So we are going to get 6 for this, 6 for this, 6 for this, 6 for all of these, right? But instead of finding it this way, all you have to do is just count the numbers in each row, right? And just multiply them. So 7 times 2 times 3 is 42, right? So we are getting 42 factors, right? Now you may think that we are taking combination of three numbers, right? Then where is like a factor which only have the product of two numbers, right? Such as 2 to the power 4 times 5 to the power 4. Now where is this number? We did not consider it. Actually, we did consider it, and in the combination where we have taken 2 to the power 4, then 3 to the power 0, then 5 to the power 4, right? So this is the combination. Now 3 to the power 0 means 1. So basically it means nothing, like the 1 multiplied to the number itself, it will be the number itself, right? So we have considered all the possible two-digit product factors, single-digit factors, and three-digit product factors with this method by adding the power zeros for all these three numbers, right? Okay. Now the question was we have to eliminate the perfect cubes, right? Now only perfect cubes I can see is 2 to the power 6 and 2 to the power 12. No other powers in all the rows have the which are divisible by 3. No other numbers have the powers which are divisible by 3. Okay, so we are eliminating these two combinations, right? Yes, and there is one more combination that we have to eliminate, which was our first combination, which is this 2 to the power 0 times 3 to the power 0 times 5 to the power 0, which essentially means 1, right? And 1 is not a perfect square. So we have to eliminate three numbers from here, which means 39 factors will be our final answer.